Welcome back to Probability and Statistics. This is chapters 8 and 10 from Elementary Statistics, 4th edition by William Navidi. We're looking at two chapters in this lesson because both chapter 8 and chapter 10 relate to this idea of confidence intervals. And a confidence interval, we'll formalize this definition in a moment, but a confidence interval is really just a set of values or a range of values that we believe captures some kind of information about the population. So, for example, maybe I'm looking at the average weight of adult men in the United States. So I create this confidence interval. Maybe it's 170 to 200, and I have a certain confidence that that range of values from 170 to 200 captures the actual mean weight of all adult men in the United States. I might be 90% confident or 95% confident, or if it's a really small range of values, maybe I've narrowed it down to 175 to 185, but I'm not very confident because it's such a small range. So maybe I'm only 60% confident in a case like that. So that's what a confidence interval is. And what we're going to be doing is looking at how to construct these in a variety of situations. Specifically, chapter 8 deals with one sample confidence intervals. So where I'm just looking at maybe like an average weight or height of a group. And then chapter 10 gets into two sample intervals. And so this is where we have two different groups or samples, and we're comparing them with each other. We want to know what is the, how do the differences, or what do we believe the difference is between those samples, whether it's the difference in means or a difference in standard deviations, things like that. And so with that, let's go ahead and get going here. And let's start off by just formalizing the definition for a confidence interval. So as I mentioned before, a confidence interval is a range of values. And so we'll kind of start with that with our definition here. So a range of values. And specifically to find that range of values, I'm going to give you kind of a generic formula, and then we're going to obviously get more in depth with this later. But it's taking what's called a point estimate. Point estimate is usually some kind of average or value that you've analyzed through your sample. And then we add and subtract the margin of error to that to come up with this range of values. So that is, in brief, what a confidence interval is. And then more to the point, it's used to estimate. It's used to estimate the value of a parameter. And again, parameter just referring to something in the population. So again, I might be trying to estimate the average weight of adult men in the United States. I might be trying to estimate the average weight of a box of Lucky Charms, right? Anything like that. So embedded in this idea then is this idea of a confidence level. And again, confidence level just says exactly that. How confident am I that this interval that I've created truly captures the actual value that I'm looking for in the parameter? How confident am I, for example, that it truly captures the actual average weight of adult men in the United States? So confidence level is a percent between 0 and 100, so it's just kind of a normal percent that measures the expected success rate of the confidence interval. So when I say, for example, that I am 95% confident that my interval captures the true average weight of men in the United States, what I'm really saying is that if I were to take a sample and find a range of and find this confidence level, and if take another sample and find a confidence interval, and take another sample and find a confidence interval, if I were to do that a bunch of times, hundreds, maybe even thousands of times, I would expect out of all of those confidence intervals that I've created, that about 95% of them would actually capture the true average weight of adult men. So that confidence level, we often will just say, I'm 95% confident, or I'm 80% confident, or things like that. But really, more specifically, it's really saying what I just said before, that if I do this a bunch of times, if I make a bunch of confidence intervals, that 95% or 80% or whatever my confidence level is, that is the percent of those intervals that would capture the actual value of the parameter. Okay, so when we can make these confidence intervals, there's two things we need to check for in order to actually use the process that we're going to look at in this lesson. First of all, we have to make sure that the sample is actually random. Now, we talked an early lesson about how to randomly sample. There's many different ways to do that. It doesn't matter what method is used as long as the sample is truly random. The other thing that we need to look for is to make sure that our sample size is greater than 30. And that's the central limit theorem that we talked about in a previous lesson. Or just very simply, I need to know that the population itself is already approximately normal. So either of those two things. Bottom line is, what that is going to do is ensure that when I take the sample, that the sample is approximately normal. If it's not approximately normal, I can't use this method for finding confidence intervals. There's other methods that exist. We're just focusing on truly where the sample is normal. All right, so let's just take a look at a really simple example. We're not going to get into any deep math or anything, just kind of really make sure that we understand this idea conceptually. So let's say, let's kind of change the context just a little bit. And let's talk about, instead of mean weight of adult men in the US, let's talk about the average weight of small dogs. Okay, now, I don't know how to define a small dog, but for purposes of this activity and this exercise, we're just going to generically call, little dogs, small dogs. All right, so let's suppose that I take a random sample of 100 dogs, 100 small dogs. Okay, so random sample of 100 small dogs. Again, I'm wondering, what is the average weight, or what do I believe might be the average weight of all small dogs that exist? So I take a random sample of 100, and what I find is that the sample mean weight, which again, remember, we would write that as X bar for sample mean. That is, let's just say it's 15 pounds. Now, again, we'll learn how to find margin of error, but for purposes of this, I'm just going to say that the margin of error I'm creating is 2.5. And specifically, that margin of error, again, is dependent on the confidence level that I've set. So in this case, let's suppose that I've also set a confidence level of 90, or let's just say, let's go lower, let's say 80%, confidence level of 80%, because this is a fairly decently sized interval, I think. Okay. So the way that I'd find the confidence interval then is, again, to take the point estimate plus or minus the margin of error. Well, in this case, the sample mean, that 15 pounds, that is the point estimate. So I'm going to take 15 and I'm going to add and subtract the margin of error 2.5. And what that gives me is this range of values, this confidence interval. And so what this means then is that I believe at that 80% confidence level that if I were to weigh all small dogs that exist, that the average weight of all of those small dogs would be somewhere between 12.5 and 17.5. So let me go ahead and write out how exactly we interpret this. So I would say, for example, if I'm going to interpret the confidence interval, so interpret the confidence interval, I would say something like I am, or we are 80% confident, because that's the confidence level that I used, that the interval 12.5 to 17.5. And I like to use the word captures. You can certainly say this in a number of different ways, but I'll explain why I like the word captures in a minute. Captures the true mean weight of small dogs. So that's how we would interpret the confidence interval. We're 80% confidence that that interval captures the true mean weight of all small dogs, right? We're talking now the population. The reason I like the word captures is because that interval represents all possible values that could be the mean at that 80% confidence level. So don't think of this as being like, well, the closer you get to the center of that range, the more likely it is to be the value. If I'm looking at a value of, so exactly in the center of that is 15 pounds, right? So I might think, oh, so I'm probably most likely going to see that the average weight is 15 pounds. Not necessarily. It could be 12.6. It could be 17.499, right? It could be any number in that range, and every single number in that range is equally likely to be the mean of all small dogs. So I like this idea of captures because I almost think of it as tossing a net over those numbers and just believing at 80% that that net is going to capture within that range of values, somewhere in that range of values, the actual average weight of all small dogs. As far as the confidence level goes, if we wanted to interpret the confidence level, um, I'll do that as well. So confidence level. Basically, what this kind of the way to think of this, and I was explaining this earlier in my example of the weight of adult men. But if we make many, so if we make many 80% confidence intervals, so ranges of numbers ranges of numbers that we're 80% confident capture the true weight, then we expect. So we expect uh, about 80% of these intervals. We expect about 80% of these intervals to capture the true mean. So I would expect, if I did this 100 times, I would expect about 80 of those confidence intervals would capture the true mean weight of small dogs. I would expect about 20% to miss the mark, that the actual mean would be somewhere outside of the range that I created. All right, so that's kind of just a simple example, just to maybe help understand and see conceptually what a confidence level is, and to start to see how these pieces kind of work together to create this confidence interval. All right, so how do we actually go about constructing this then? So in order to construct a confidence interval, again, I've mentioned that we take the point estimate and we add or subtract this thing called margin of error. Something you're probably familiar with conceptually, but we're going to define mathematically how we find this in the context of these problems. So margin of error, to find that, we have to take what's called a critical value and multiply it by the standard error. So if I kind of keep breaking this formula down, I'm going to say that it's the point estimate plus or minus some critical value times the standard error. And how we find that looks like this. Point estimate is going to be the mean of something. It might be the average weight. It might be the average height. Whatever it is, and then we're going to add and subtract. The textbook in the textbook. William or Navidi uses a symbol that I'm honestly not real familiar with. He kind of writes this Z and then like this A over 2 subscript. I am more accustomed to seeing it written like this kind of Z star. So if you remember in a previous lesson, we talked about Z score. And Z score and Z star are basically very closely related. We just use a symbol like a star or a subscript to denote that we're not actually talking about Z score. We're talking about Z as a critical value in this context of the problem. Okay, so we're going to actually be using some of the tables that we've seen before to find these values, but we're just going to just throw that star on there for purposes of this. So that's the critical value, and then we find the standard error. Standard error is taking the standard deviation of the population and dividing by the square root of n. Now, there's two situations that arise with this. One is where we know the standard deviation for the population, and one where we don't know the standard deviation for the population. So I'm going to go through both methods and show you how to deal with both of those as we look to find a confidence interval. All right, so let's take a look at an example. And we're going to start with the situation where we know the standard deviation for the population. So in this case, it says to estimate the average weight of an Oreo cookie, 50 cookies are randomly sampled and weighed. The sample mean is 11.19 grams, and the population standard deviation is 0.082 grams. Construct a 95% confidence interval to estimate the true mean weight of an Oreo. Okay, so again, before we even get going, we remember that we do have those checks that we need to test before we jump in and find this confidence interval. So we need to, first of all, just acknowledge that, and I'll just kind of write checks here. We need to acknowledge that this is a random sample. And we also need to just kind of evidence that our sample size of 50 is in fact greater than or equal to 30. And that again satisfies the central limit theorem. That means that we can assume that our sample is going to be normal. And that's key for doing these problems. Okay, so with that established, with those 2 points established, again, we are finding our confidence interval by taking x bar plus or minus z star times standard deviation over the square root of n. Okay, so x bar, again, that is the mean of the sample. So the mean of our sample is 11.19. You see that at the top there. So we are going to take 11.19 plus or minus, and now we need this z star score, okay? So in this case, we are constructing a 95% confidence interval. There are different ways of doing this, but basically what we are going to do, if you think about kind of what that means, if I draw a picture, we know that this is normal, or at least we're assuming that this is normal. If I think about a 95% confidence interval, 95% in a normal curve basically goes out 2 standard deviations, okay? Leaving 0.025 or 2.5% here and 0.025 or 2.5% here, okay? When we looked at z-score in a previous lesson, we used a table to find the area under the curve given the z-score. We could do something similar here, but I'm going to show an easier way to do this. So we could use a table, the same table we used to find z-score, but that requires that you actually kind of map this out and figure out what that tail percent is, because if you remember with the table to finding z-score, it only gives area to the left of your defined area. So this is the area to the left. I would have to find that specifically in the table. There's an easier way. There is another table, and we're going to be using this more extensively throughout this lesson, but we're finding z, but this table is actually used to find what's called t. And so so we had a z distribution critical values. This is a t distribution for critical values, okay? We're not using this like the Z table, but at the very, very bottom of most of these tables, so if you find a T table like this, most of these at the very, very bottom is going to have a row that says infinity. And I'm going to explain what all of this means in just a minute after this example. But just for now, just to see where we find this Z star, what we're going to do is it says confidence level down at the bottom of this particular chart. It says confidence level C. What I'm going to do is find the confidence level for our interval. We're doing a 95% confidence interval. And I am simply going to look at the number directly above it in that infinity row, 1.960. That is the value that we're going to use for z. Now, if you were to look in the actual z table, what you would be doing then is you would be looking in that body of, like you kind of like this, you got this whole body of values. You would find your z score and you would hone in on the value for that z score, and that would also give you the 1.96. So you could use the other table. I just think this is much faster, much simpler. Our z is 1.96. So let me head back up to the example here. And so we're going to plug in 1.96. And then we're going to multiply that by the standard deviation divided by the square root of the sample size. So again, we are given the fact that the standard deviation for the population is 0.082. And we are dividing that by the square root of 50, which was our sample size. So just using a calculator to kind of punch this all out, what we're going to get is an interval from 11.17 to 11.21. Okay. Again, Navidi in the text will sometimes write it as 11.17 is less than the population mean. So the mean weight for the population of all Oreo cookies is less than 11.21. So you can kind of think of it either way, just this kind of interval notation with the parentheses, or as a true inequality, where we're just saying that the population mean, right? The population mean is between those two values. All right. And in words, what we're saying again is we are 95% confident. We are 95% confident that the interval 11.17 to 11.21 captures the true mean weight of an Oreo cookie. Now, notice that that's a pretty tight range. I mean, 11.17 to 11.21, that's only 0.04 of a gram. I believe we're in grams here. And yet we are 95% confident in this example. And the reason for that is partly really in large part because of our sample size. The larger your sample size, think about your formula here. So I take a sample size, I find this mean weight of 11.19, right? I just measure all the Oreos that I gathered, I weigh them, I take the average weight, and I get 11.19. The confidence level simply is going to determine kind of how wide or narrow we're ultimately trying to make this. So again, the more confident I am, the more narrow, the more wide my values are going to be. The less confident I am, the more narrow it is. Okay, because the more narrow it is, the less likely it is to contain the actual mean, and therefore I'm less confident. Okay, so obviously our confidence level is what determines the z score here that we use, or the z star that we used here. But this is also driving the value, the margin of error, because as my sample size gets larger, I'm going to be dividing by a larger number. Dividing by a larger number makes this fraction smaller, which makes the overall margin of error smaller. So as my sample size gets larger, my margin of error gets smaller, and it's going to create a much tighter range of values. If I take a small sample size, it's not necessarily going to be as accurate, and therefore it's going to create a wider margin of error to kind of meet the demands of that confidence level that I'm looking for. All right, hopefully that makes sense. And so what I want to do is transition now and talk more about this idea of T, because T is going to play a part now in a lot of what we do throughout this lesson. So as I mentioned, When we find a confidence interval, knowing the population standard deviation or not makes a difference. So think about standard error. Standard error is the population standard deviation divided by the square root of n. Okay, so again, this is knowing the population's standard deviation. If I try to use a standard deviation for a sample, so let's suppose I didn't know the population standard deviation, obviously I can't use this formula because I don't know sigma, right? So I wouldn't be able to do this. But I would always be able to calculate the standard deviation for a sample because when I take the sample, I'll have that raw data and therefore I can find the standard deviation. So if we try to use, I'm going to actually write this out. If we try to use this sample standard deviation instead, so S divided by the square root of n, it's not normal. What actually happens, if you think about when we sample, even if the population is normal, so let's just take a population, right? I've got a population that's normal. We know that most of the data is going to be gathered towards the center, and then less data as we trail off to the ends. When we look at standard deviation for the population, the standard deviation accounts for every single value under that curve. But when I take a sample, I'm sampling within that curve with the assumption that my sample is representative of all the data in that curve. When I take a sample of 50, though, I'm expecting a lot more of those numbers to be in the middle and very few to be out towards those other edges, just from a probability standpoint. So because of that, when I calculate the standard deviation for a sample, it is likely going to be smaller than the standard deviation for sigma. So in other words, we typically would find that S is going to be less than sigma because I'm not necessarily getting those extreme values that would make a larger standard deviation. Okay. So because of that, what ends up happening then is the curve for my sample isn't necessarily normal. So if this is, let me kind of just draw a larger normal curve here. So if this is the normal curve, my sample curve might look something like this, where it's maybe a little bit higher in the middle and looks something like that. Now, as I take a larger sample size, it should get closer and closer and closer to looking normal. So this might be for a sample size of, let's say 20. If I take a sample size, and actually make that even smaller, let's say this is just a sample size of 5. If I take a sample size of 10, I'm going to expect that it's going to maybe look something more like this, right? Where this is now n equals 10. And as I make my sample size larger and larger and larger, I'm going to get closer and closer to actually getting something that is or close to normal. All right. So when, to kind of summarize all of this, when our standard deviation for the population is unknown, we use the sample standard deviation. So we use SX sampled for the sample standard deviation, and we use T, not Z, for our critical value. And in just a moment, I'm going to take us to the chart. I'm going to show why we use T and basically what T is doing, or what that chart is doing to kind of accommodate the fact that we don't have a perfectly normal curve in a smaller sample size. And what that kind of plays into is what's called degrees of freedom. So degrees of freedom simply refers to our sample size. Okay, so degrees of freedom for our purpose is going to be n minus 1. So we're going to take our sample size, we're going to subtract 1, and that's going to give us degrees of freedom. Now, you don't need to know why, quite honestly, and you don't need to know how to find degrees of freedom. Just simply know that degrees of freedom is a value that we use with the t-table, and it relates directly to our sample size. So let's go ahead and take a look at that table again that we referenced earlier. So in this table, again, uh, note a couple differences here. First of all, unlike Z, this is actually finding the probability to the right. It's actually going the opposite direction as Z. So you kind of see that up in the picture here. The other thing is let me go down to the bottom. So remember when we did that example, and I said we were going to do a 95% confidence interval, and we knew the standard deviation for the population already. And so we used this value of 1.96. Now, remember, what we're doing with that number is we're multiplying that by the standard error to get the margin of error. So this number is a multiplier. And as a multiplier, the bigger it is, the wider our interval. The smaller it is, the smaller our interval. Okay. So what happens is you'll notice that this is for basically a sample size of infinity. In other words, you've basically sampled the entire population. As the sample size goes down, this left column is our degrees of freedom. This is the DF on that left column going down. So you'll notice as the degrees of freedom get smaller, as we go up that chart, in other words, my sample size gets smaller and smaller and smaller, it is more and more likely that the standard deviation for the sample gets smaller than the standard deviation for the population. So to compensate for that, notice that the t-values are actually getting bigger as we go up that chart. So as your sample size gets smaller, t gets bigger to compensate and basically to stretch out that interval to compensate for the smaller standard deviation. Okay, so hopefully that makes sense. Bottom line is when we don't know the standard deviation for the population, this is the table that we want to use. And this table basically, like Z, you're going to cross-reference, but unlike Z, where you just look for you're looking for your decimals, this one you need a DF. So you're going to find your DF, and then you're going to go across. You could use the tail probability at the top. I would just go to the bottom and use the confidence level at the bottom. Okay. And so we just look at 95% or 90% confidence level, whatever that happens to be. All right, so let's take a look at an example then that is where we don't know the standard deviation for the population, and kind of contrast that with the one that we did earlier where we did know. So we're going to use the exact same example that we did before, and we're going to randomly sample 50 Oreo cookies. We've got the same sample mean. But again, this time we don't know the standard deviation for the population. So we are going to use the standard deviation for the sample. And just to remind us, so this population, these numbers are just made up, but the sample population was 0.082. That was the standard deviation for the population. Our sample size, our standard deviation is a little bit smaller here. That should be 0.076, not 0.76. Sorry about that. So 0.076. And we are going to construct a 95% confidence interval for this. Okay, so to do that, again, same process that we did before. The only difference is that we are going to go to the chart to find these values. Okay, so we'll take 11 point. Well, first of all, let's find our DF. So our DF is going to be sample size minus 1, or 49. And again, we're using a 95% confidence level for this activity. So right here, 95%. So if I go to the chart, 95% DF of 49. In the chart, as you go down, it's going to go by ones, but eventually when you get down to 30, it starts going 30, 40, 50, 60, and so on. It's going to start skipping over numbers. And you'll notice that there is no 49. Again, we always want to give what we call a conservative estimate. So I'd rather be conservative and give a wider interval rather than a smaller interval. So if 49 is somewhere between 40 and 50, even though it's only one away from 50, I'm going to go down to 40 and be conservative in creating a wider interval than I know I would actually get if we had the values for 49. We're doing a 95% confidence interval. And so I just cross-reference those, and the number we're going to use is 2.021 for t. So that is our critical value, 2.021. All right, so t, 2.021. All right, so we can go ahead and find our confidence interval now. So we're taking x bar plus or minus. In this case now t star, because we're using t, not z, times the standard deviation for the sample divided by the square root of n. Okay, I'm going to just kind of highlight this. This is the formula we want to use, again, when we don't know the standard deviation for the population. So in this case, we're going to take 11.19. That's the mean weight of our sample, plus or minus 2.021 times 0.076 divided by the square root of 50. And that gives us then an interval of 11.17 to 11.21. All right. Now, actually, I think if we go back up and look, I think that might be the same interval. That is actually almost the exact same. If we round it out further, we'd probably find a little bit of difference. That is complete coincidence. These numbers I just kind of made up based on what I thought might happen if we took a sample. Again, knowing that the sample would give us a smaller standard deviation. Um, and notice that t-score really did its job. It did exactly what it should have done. It took that smaller standard deviation and it stretched it out just enough that it basically gave us the same interval that we got before. All right. So that's how we find confidence intervals, both when we know the standard deviation for the population and when we don't know the standard deviation for the population. Okay, so let's switch gears a little bit here, and we're going to look at how to find a confidence interval for a proportion. So we're still in the one sample world. We've looked at one sample for a mean. Now we're just going to look at a one sample for a proportion. So in this case, when we want to find the interval, what we are going to is similar to when we have a mean, but in this case, we still have point estimate plus or minus margin of error. That as a kind of a global formula still works. So it's point estimate plus or minus margin of error. But how we find, again, this information is going to be a little bit different. So point estimate in this case is no longer a mean. It is going to be the proportion for our sample, plus or minus. And now we are going to go back to Z. So we use T when we are doing a mean. We use Z when we're using a proportion. Okay, so Z star and then margin of error. That formula also looks a little bit different. We take the proportion times 1 minus the proportion, proportions for the sample specifically, divided by the sample size. And this part is, again, what we call standard error. It's like standard deviation, but something that we're calculating based on the sample. And then just to clarify also, again, p hats, p with kind of that upside down V, is just our sample proportion. You would very, very, very rarely, if ever, have the population proportion. Otherwise, we wouldn't need to do this process. So, all right. So when we do the interval for a proportion, again, there are some things that we need to check for, some assumptions that we are making here. We always want a random sample. So really, in any of these things that we're doing, we always want to make sure that our sample is random. In this case, we also want to make sure that our sample is less than 5% of the population. Now, let me just pause for a minute, because you might think, well, then does that mean that bigger sample sizes are worse? Because this is kind of saying we want a small sample size. And the answer is no. You actually want a bigger sample size. The bigger the sample size, the better. It's just that there are other ways of calculating intervals for large sample sizes. So this type of process that we're doing here is intentionally made for smaller sample sizes. We would have to switch to a different process if we had a much larger sample size compared to the population. The items in the population are divided into two categories. Now, this isn't something that we actually have to write out or formalize as a check, but we just want to make sure that our data fits into one of two categories. And then the third is that the sample is greater than 10 in each of those categories. So if I have a sample of 50 and maybe 30 of those are in one category, 20 are in the other, I'm okay. But if 45 are in one category and only 5 are in the other category, again, I really shouldn't be using this process for that situation. So what we'll really primarily check are just the first two. We're going to check that it's random. We're going to check to make sure that our population is less than 5%. This one we really don't need to check, and we may check, if it's not obvious, we may just formalize the fact that the samples are big enough within each of those categories. All right, so let's look at how this is done then. And again, we're just going to be really relying on this formula that I just wrote out, the p hat plus or minus, to do this. So in a study done by the Annenberg Foundation, a random sample of 1,416 U.S. adults were asked to name the 3 branches of government. 36% of those sampled answered correctly. Construct a 90% confidence interval for the proportion of adults who can correctly name the 3 branches of government. Okay, so we asked this question, people answer, they either answered correctly or they didn't answer correctly. So those are our 2 groups, right? They were either right or they were wrong. The other things that we'll check here then are the random. And again, it does say that it's a random sample, so we're good there. And we want to make sure that the sample size is less than 5%. Some textbooks will use 10%. So if you hear me say 10% incorrectly, that's just because other books use 10%. Navidi chooses to use 5%. So we need to make sure that 1,416 is less than 5% of the U.S. adult population. Well, if you think about it, that's going to be pretty clear. I mean, we've got 100 million plus U.S. adults in the United States. I think 1,416 is far less than 5% of that number, so we're good there. And then obviously with a sample size this large, of course, the 2 categories are both going to be bigger than 10. So again, I wouldn't necessarily check it for this one. All right, so let's go ahead then. We can go ahead and use this process. We're going to take p hat plus or minus z star times the square root of p hat times 1 minus p hat all over the sample size. All right, so in this case, p hat is going to be the 36% who responded correctly. Okay, so we're going to take 0.36 plus or minus z star. This is where we have to go back to that same table that we've been using. We're going to go back to that t table. And so in this case, if I want a 90% confidence interval, now I'm looking at 90%. And again, for z, we go to that number right above it, 1.645. So that's what we're going to use for z, 1.645. Let me find my example here again. So 1.645. And then times the square root of, again, p hat, which is 0.36, 1 minus p hats, which of course you could just write 0.64 if you wanted to, divided by this sample size 1416. So that's our setup for finding the interval. That would give us an interval of 0.342, so that should be a 2, to 0.378. All right. So again, what we would say here is that we are 90% confident. That was our confidence level. We are 90% confident that the interval, 0.342 to 0.378 captures the true proportion of US adults, who can correctly name the three branches of government. All right. So again, when we think about intervals, any value in that interval is equally likely to be the true proportion in this case. So it could be 0.342, it could be 0.378, could be anything in between. But that is our confidence interval for that example. All right, one last thing we're going to do here before we jump into two samples, and that is to figure out if I have certain information, I know my confidence level, maybe I even know what I want my margin of error to be. So I've kind of said, maybe I'm in a manufacturing situation and there's a threshold of error that is allowed. But anything outside of that threshold is not allowed. Anything beyond a certain level of error, we'd have to shut down the machine, recalibrate, and start it up again. So if I'm the quality control person taking samples to determine whether or not we're within that margin of error, sample size can become important. And so this is really getting into then how do I determine what sample size I should be taking in order to know that my results are reliable in the sense of telling me whether or not we are within that threshold of margin of error or not. Okay. So for a mean, if we're doing this for a mean, if you think about the formula, all we're going to do is just rearrange the formula for finding a confidence interval and solving for n. Now, we don't need the whole formula. What we really need is just the margin of error, because that's where the n is found, the sample size. So margin of error is equal to z star. Again, this is if we know the standard deviation. If we don't know the standard deviation, we'd have t, right? So you might have t star here if you don't know the standard deviation, times the standard deviation divided by the square root of n, okay? And again, you might have to use Sx here if you don't know the sigma. All right, well, now we're just going to take this formula and we're going to solve it for n. So for example, I could multiply both sides by the square root of m. I'm going to just abbreviate margin of error, MOE, times the square root of n equals z star times sigma. And then I could divide both sides by the margin of error. So square root of n is z star times sigma divided by the margin of error. And then just square both sides. So n is going to be z star times sigma all over the margin of error squared. So that would be a formula that we could use to find the sample size that we should be using based on the confidence level, which informs us of z, and the margin of error. All right. So just as a quick example to that, 50 cereal boxes are randomly sampled and weighed with a sample mean of 0.4 ounces. Estimate the number of boxes that must be weighed to construct a 95% confidence level or interval, with a margin of error of 0.1. Okay, so in this case, we are going to set up n equals. Now again, 95% confidence interval, if I go to the chart and I look up 95%, 95% is that number right above. So in this case, 1.960. And so we'll plug that back into our formula, 1.960. 1.960, here we go. All right, times the mean of 0.4. I'm sorry, this is not a sample mean. This is the This should be the standard deviation. My bad. I really apologize for that. That should be standard deviation of 0.4. And then divided by the margin of error 0.1, and we square that entire quantity. Okay? And so what that ends up giving us then is 61.47. Now, again, we're talking about a sample size here. And so in this case, we will always round up. Obviously, samples would have to be whole numbers. But we all, again, it's kind of that conservative estimate idea that I've mentioned before. We round up. And so in this case, we'd want our sample size to be 62 boxes to meet the criteria for this situation. All right. Now, just real quickly then, for a proportion, if we were to solve that formula for n, I'll just give you kind of the jump right to the formula here. So n would be p hat times 1 minus p hat times z star divided by the margin of error squared. So that would be the formula for finding n for a proportion. In this case, if you didn't know the proportion, if you didn't know p, you would use 0.5 if p hat is unknown. And what that does is that would give you kind of the most conservative or largest value for n if you use 0.5. All right, well, let's jump forward now and let's talk about how to find confidence intervals for two samples. And so everything we've done up to this point has been for one. All right. So in this case now, what we are looking at is a situation where we have two different samples. We've taken two different samples, and we want to know if what would the difference be between those? So we might be looking at a difference in averages or means of those two samples. We might be looking at a difference of proportions for those two samples. So the confidence interval here, it's going to look similar to what we've done. What we're doing, though, is really just this idea of combining multiple samples together. And so, for example, to find the confidence interval, if we're doing this for a mean, I am going to take, write this out, confidence interval. I'm going to take x bar 1 minus x bar 2. And then plus or minus, we're going to assume here that we don't know the standard deviations, so we'll just use t right away. And then the square root of s sub x1 squared over n plus s sub x2 squared over n2. Okay, so let me kind of walk through and just talk about a couple of things here. So the first part of it, this is really our point estimate. So if you think to one sample, this would have just simply been x bar. It would have been the mean of our sample. Well, now we have two samples and we want to look at the difference between those samples. So this is really just the difference of the means of those samples. So it's the difference of the means of the samples. Okay, and then t, of course, is our critical value. And in this case, again, we need a df. Now, we've got two samples, though, and what if those sample sizes are different? So in this case, df, when we do n minus 1, we always use n for the smaller sample size. So we'll use n for the smaller sample. And then the last part of this is a little bit different because now we're square rooting and doing all of that. There was no square root when we did this for one sample. It was just s sub x over n. Here's why we have a square root. Remember that what we're dealing with here now in this last part of the formula are standard deviations. We can add and subtract means, which is exactly what we're doing in this first part of the equation. We're subtracting two means to find the difference. But you cannot add or subtract standard deviations. It just doesn't work. What you can do, though, is you can add variances. And remember that a variance is simply the standard deviation squared. So what we're doing is we're taking from the formula For a single or for one sample, we're taking that part of the formula S sub x over n, and we're squaring it basically to find we're squaring the standard deviation to find variance. We then divide by n. We do that for the second sample. We square its standard deviation, divide by n. Now, of course, these are different samples, which is why you have the ones and the twos. We add those together, but those are values that are squared, right? They're squared standard deviations. So we square root to bring it back from variance to square root, okay? Or I'm sorry, back from variance to standard deviation by taking the square root. So that's what that formula is doing. That's why that formula looks the way that it does, okay? It's basically beyond that, just kind of a plug and chug situation. You've got all the information, you plug it in, that's going to give us that confidence interval. Okay, so let's go ahead and look at an example of this. And again, we've got the same assumptions here, random samples. The middle one, again, we don't really have to typically worry about. You just want to make sure that the samples are independent of each other, that sampling for the one case does not impact sampling for the other case, okay? Whatever that might look like. And then again, we need central limit theorem here that the sample is greater than 30 for each sample, or that the population is approximately normal. All right, so the same test is given to two different classes. Class A has 28 students. Class B has 25 students. Class A had a mean score of 82 and a standard deviation of 3.4. Class B had a mean score of 87 and a standard deviation of 2.6. Assume the population distribution is approximately normal. Construct a 95% confidence interval for the difference in mean test scores between A and B. All right, so just real quickly, our checks. So we're really just going to check two things again, like we did with the one sample. We are going to check to make sure that our samples are random, and we are told that they are random samples. And then again, the second thing that we would test for is that both samples are greater than or equal to 30. But in this case, they're not, right? We've got one class had 28, the other had 25. Those samples are not big enough. However, they tell us that the population is normal. So that's the other way we can satisfy that second condition. The fact that the population is normal or approximately normal is enough for us to know or to assume that our samples, even though they're a little smaller, are also going to be normal. All right, so with that checked, we can go ahead and set up our confidence interval. So we're going to take the difference in means. So I'll just use A as kind of A, x1, B is x2, and so on. So we're going to take for our interval the difference in the means. So that's going to be 87 minus 82, plus or minus. All right, so again, we need a t-score here. We're going to do a 95% confidence interval. Our smaller sample is 25, so our DF here is going to be 25 minus 1, or 24. So we're going to go to the chart. We're going to look up a confidence interval of 95% for a DF of 24. If I can get my technology to work for me, here we go. All right, so 95% DF of 24, and we are using 2.064 for our t value, 2.064. All right. So that's t star. And then times this big old square root, where we have to take the standard deviation of A, square it. Again, that's making it into a variance. Divide by its sample size. Add the standard deviation for B, which was 3.4. Square that to put it into variance. Divide by its sample size of 28. Oops, I'm sorry. The first one should be 25, not 28. So 25 here, 28 for the second. And then again, we're square rooting to take what is now variance and bringing it back to standard deviation. And that would give us an interval of 3.29 to 6.71. So again, we are 95% confidence that the difference in means, or I'll say in mean test scores, between Class A and Class B is between 3.29 and 6.71. You'll notice my wording has changed a little bit from how I've interpreted confidence interval before, which is absolutely fine. I could interpret this exactly how I've done before. We are 95% confident that the interval captures the true difference in means of test scores. Again, it doesn't really matter how you write it. You just want to capture the essence of what's happening here. All right. So basically, then there is a second part to this, because what we're really asking is it's not really written this way, right? It doesn't tell us specifically, but why would we be comparing means of these two classes? Well, most likely we're interested in whether or not one class did better than the other, whether because of the students or the way they were taught or whatever the case might be. And so when I look at the results and I look at that interval, because the interval is entirely positive, and we took Class A minus Class B, in order to be positive, A would have to be bigger than B. And the fact that my interval is positive tells me then that we have evidence. We have evidence that Class A scored higher than Class B. Or that Class A did better than Class B, or however you want to say that. But we have evidence that A outperformed B because that difference is in fact positive. We're 95% confident that A outscored B on average somewhere between 3.29 and 6.71 points on that test. So to summarize that idea, when we get our interval, let's suppose that we do A minus B, whatever A and B happen to be. If the interval is positive, so two positive numbers like we had in our example, again, that would tell us that A is larger than B. Might be that A is better than B, higher than B, whatever it might be, but A is a larger average than B overall. And we're confident of that to whatever that confidence level is. If they are both negative, then we know that B is larger than A. And if you would get something that is negative positive, in other words, this includes 0, then we have no conclusion because of the fact that it includes 0. And this can be a little bit confusing sometimes. So let me give you a very specific example. If I have an interval that is, let's say, negative 0.1 to 5.98, many people would look at that interval and go, oh yeah, A is definitely better than B, because look, you've got 0.1 in the negative and almost 6 in the positive. Clearly, the chances are better that the answer is positive than it is negative. So yeah, clearly A did better. Well, remember, every single value is equally likely to occur. Negative 0.1 is as likely to occur as any other value in that interval. And so we have to assume in this case that we don't have a conclusion, because it could be that it is actually negative 0.1, or it might be negative 0.001 or negative 0.090, right? So the part of the issue is when we think about probabilities, we often think of probabilities in very small scopes, whole numbers, or maybe even 1 or 2 decimals. But you have to remember that between every number is another number. And so technically there are an infinite number of numbers in this range. And so to try to say, well, the area or probability of getting a positive is greater than the area of getting a negative, well, not so much. It's not that easy. So anytime, no matter how much the the values maybe teeter into one side or the other. If you have a negative and a positive, it is always no conclusion. Now, if I have something this close where I'm like, whoa, if that had just been a shade higher, we would have had evidence to the fact that A did better. Maybe you run another sample or a few more samples just to confirm and verify that this is in fact accurate. Okay, there is another way that we can look at two sample situations. So we just looked at a situation where we had two samples. We found the mean of one sample, we found the mean of the other sample, and we compared those two means with each other. Sometimes it makes more sense to compare the differences between individuals and then look at the mean of all of those differences. So where this is typically going to happen is when you have a situation where maybe you're doing like a pre-test and a post-test, and you want to look at the individual changes by a student, or you're looking at maybe an exercise program, and you want to see if it's making a difference in weight loss or in heart health or something like that. So you pre-test or take initial data for a participant, run your health event, and then take data on the participants after, and you want to compare a patient to him or herself, and then do that for the next patient and the next patient and the next patient or participant, and then find the average of those differences. Okay, so this is what we call paired samples, because we're pairing within those samples. We're taking a person from the first sample, their data, and then pairing it with their same data from the second sample. All right, so that's what a paired sample is. And again, for a confidence interval, so it's going to look a little bit different now because we don't have a difference of means. We're not finding two different means and and subtracting them. We have one mean, and that is the mean of the differences. Okay, so this is, we're going to define this as the mean of the differences versus before, where it was a difference of the means. Hopefully that makes sense, that subtle difference there. Plus or minus t star times the standard deviation for the differences divided by the square root of n. Okay, and so again, S sub d is the standard deviation. I'll abbreviate that, but standard deviation of the differences. All right, so let's take a look at an example of this. So a group of 5 individuals with high blood pressure were given a new drug designed to lower blood pressure. The systolic blood pressure for each individual before and after treatment are shown below in the chart. Construct a 98% confidence interval for the mean reduction in systolic blood pressure. Okay, now we don't obviously meet some of the conditions here. This is, in fact, we really don't meet any of the conditions, right? Because this is not random. And we don't have large enough sample sizes. For purposes of this example, that's okay. We're going to keep moving forward with that. The other thing to mention is, in a situation like this, you're not going to have random because we've asked people to participate in an experiment. And you can't force people into an experiment. So you can't then have a random sample if you aren't randomly just drawing from a population, right? You've got to invite people in, and they have to say, yes, I volunteer to be part of this, and you've lost that sense of randomness. But in this kind of a situation, that's actually okay. There are other things we would do then to mitigate maybe some of the things that randomness does for us. Okay, let's go ahead and just take a look at this. So basically what we need to do first of all is we need to find the differences. We have the before, we have the after, but we need to find the difference in each of those. So I'm always going to take, in this case, before minus after. Actually, I guess it would make more sense to do after minus before, because we want to see, we're hoping to see a lower number here, or we want to see the difference from before to after. So if I do after minus before, we're going to have minus 25, positive 32, a positive, negatives. I'm going the wrong way here. Negative 32, negative 39, negative 23, and negative 38. Okay. Now, you would use some kind of software to find the mean and standard deviation. You could use Excel. You could use a graphing calculator if you had one, some other software, statistical software. But bottom line is, if you were to find the mean and standard deviation for the differences, you would find that the mean difference is negative 31.4, and the standard deviation of those differences is 7.301. All right. We also need a df in this situation, and df again is going to be n minus 1, which is just going to be 5 minus 4 or 4. It's going to be 5 minus 1 or 4. Okay. All right, so we've got the mean of our differences is negative 31.4 plus or minus. Now we're doing a 98% confidence level here with a df of 4. So again, if I go to that table and I find a df of 4, 98% down at the bottom is going to be, let's see, 2 over, and so it looks like it's this number right here, 3.747 is going to be our T star. So 3.747. So 3.747. And then times the standard deviation of the sample, 7.301, divided by the square root of 5, the square root of our sample size. And that gives us an interval of negative 43.63 to negative 19.17. So again, we are 98% confident. We are 98% confident that the interval negative 43.63, negative 19.17 captures the true mean difference. I'm sorry, difference in means, right? We switched to difference in means. Some true mean difference, or true difference in means for systolic blood pressure. And in this case, because it's negative, negative, we do have evidence that it was that the drug basically reduced blood pressure, correct? So we went from a higher to a lower, doing A minus B. B is larger. We have evidence that B was larger, and therefore that the after is smaller. So we have evidence. That blood pressures decreased after using the drug. Now, I want to caution that, if this was truly set up as a proper experiment, we'd also have evidence that it actually was the drug that caused those changes. But if we didn't set up the experiment properly, we would have correlation, but not necessarily causation. So we would just want to be careful about how we interpret that. Okay, let's get into proportions and wrap up with this idea. So we're going to stay in this world of two samples, but now we're going to go to a difference between proportions. So again, the formula is going to have some similarities to the one we looked at earlier for one sample for a proportion, with just some slight differences. So we're going to take the difference in proportions, so P1 minus P2, plus or minus. Again, we're back to Z. So proportions will pretty much always use Z. Means will pretty much always use T, unless you know your standard deviation for the population. And frankly, that's pretty rare that you would know that. P hats, 1 minus P hats. And that would be for the first sample divided by N1. And then plus P2 hat, 1 minus P2 hat divided by N2. So that is our formula for this one. So again, we've got our assumptions, same as before. Random samples for each is less than 5% of the population. You can divide it into two categories, and each sample is greater than 10 within those categories. All right, so according to phys ed, Black and Hispanic females are underrepresented in STEM programs compared to non-STEM programs. A certain university would like to see if this is true for their students. They took a random sample of 300 STEM students and found that 12 were Black or Hispanic females. A separate random sample of 500 non-STEM students had 75 Black or Hispanic females. Construct a 95% confidence interval for the difference between proportions of Black and Hispanic females in STEM and non-STEM programs. Okay, so bottom line is we have a situation where there is question as to whether or not Black and Hispanic females are underrepresented in STEM programs. We've got some data that we're going to use to see if there is support or not for that claim. So the first thing we need to do, because we don't actually have proportions here, we need proportions first of all. So P1 hat, we'll use that to define STEM students. So there were 12 Black or Hispanic females in STEM programs out of the 300 sampled, which is 0.04 as a decimal. Okay, so these are in STEM. And then P2 is going to be the 75 Black or Hispanic females that were not in STEM out of the 500 sampled. So that's 0.15. And these are not in a STEM program. Okay, so again, finding our proportion, we're just plugging into this formula. So P1 minus P2, so 0.04 minus 0.15. Sometimes I like to put that in parentheses just to remind myself that that's kind of just that first part of the formula. And then plus or minus Z. Well, eventually you are going to remember, because a lot of these problems like this, in textbooks and in academia in general, like to use 95% confidence. So you'll kind of catch on pretty quickly that 95% confidence is a Z of 1.96. So I'm not going to go to the chart for that one. And then we have P1 0.04 minus or times 1 minus P1 divided by the sample size of 300, and then plus P2 times 1 minus P2 all over its sample size. And that gives us an interval of negative 0.148 to negative 0.072. All right. So I'm not going to write this out, but again, we are confident, right? We're 95% confident that that interval captures the actual difference in proportions of Black and Hispanic females in STEM versus not in STEM. And specifically, again, because they are negative, and we took in STEM minus not in STEM is bigger, right? So we have evidence. And I haven't been using the word convincing here, but technically we have convincing evidence. When we do something like this, we would actually say that we have convincing evidence, statistically speaking. Now, people can refute this, people cannot believe it, but statistically speaking, our evidence is statistically convincing that Black and Hispanic females are indeed underrepresented in STEM programs. All right. Now, again, that's at the 95% confidence level. So, which is a pretty high confidence level. If we wanted to, we could raise that confidence level. We could do this for 98%, and see if we end up with the same results and kind of have even a higher level of confidence. If I said I'm 70% confident that Black and Hispanic females are underrepresented, Well, people might start to look at that and go, yeah, 70%, but that leaves 30% wide open for the fact that they aren't. So when we think about this the confidence level, the 95%, the 98%, the 80%, whatever it is that you use, we want to really be thinking about what level makes sense for the situation. In this case, I think 95% seems appropriate. If I'm curious about the average distance or the average difference in weight between an Oreo cookie and a Chips Ahoy, not really that life changing, maybe 90% or something, or even 80%. If I'm talking about evidence in a trial that may convict somebody of murder and send them to jail for life or possibly even to death, um, I, I want a really, really high confidence level. Right? I want a 99, a 99.5, a 99.9. So we start by choosing the confidence interval that we want. And then we do all of our data collection and analysis. We don't do it on the back end and say, wow, look, my data, I could actually bump this up to 98%. My data would support that. That's not how it works. You set it in advance, and then you go ahead and see how the data plays out. All right. Well, that was a long lesson, a lot packed in there, but that's everything that you need to know about confidence intervals, both one sample and two sample. And so thanks for watching, and I hope to see you in the next one.